Welcome everyone to our YouTube channel AgriAddict, and I welcome you all to the discussion part of the weekly mock test. This includes the mock test 3, mock test 4 and mock test 5. The important question that is most expected in the exam. So these are the topic that will be covered here is soil chemistry, and then fertility and the soil biology. So here our first question is the fraction of humus which is soluble in alkali but not in acid. Okay, so here is the first question: which fraction of humus is soluble in alkali but not in acid? So for this we have to know the fractionation scheme of organic acids. First we have to take soil, then we have to reflux with methanol and benzene. Then what happens is whatever we get from that, then we after reflux there is a residue that we found, okay, and the soluble non-humic substance also we found. We discard this amount, that is the soluble non-humic substance, and after that the residue part then is extracted with the dilute alkali, that is maybe sodium hydroxide or sodium carbonate, and by this two component we get here, that the soluble two fraction, that is soluble organic fraction and also the insoluble organic fraction. This insoluble organic fraction is actually humin, okay, and the soluble organic fraction again it is treated with the dilute HCl, which pH is 2 to 3, important to remember. And with the treatment with dilute HCl, again two components we get. The first is insoluble fraction and another is soluble fraction. The insoluble fraction here is humic acid and the soluble fraction is fulvic acid. So three questions come from this scheme, three different type of questions, that what is the component in the soil humus that is soluble in the reflex pathway or a reflex procedure, that is the non-humic substances that we discard here, and after that whatever the residue is left, then the residue will be extracted with a dilute alkali. So what are the components that are diluted in alkali? So the soluble components that diluted in alkali are humic acid and fulvic acid. It is humic acid and fulvic acid. Both get soluble in extract with the dilute alkali, but the insoluble part is the insoluble fraction, that is humin. So humin will not get. If the question comes what is the part of, what is the fraction of organic matter which does not get soluble in the dilute alkali, so that will be humin. And after solubilization of the or extraction of those humic acid and fulvic acid by the extract with the dilute alkali, then it again treatment of dilute acid is done, and in this case the insoluble part is humic acid and the soluble fraction is fulvic acid. So the question was, what is actually soluble in alkali but insoluble in acid? So humic acid will be the answer, because it is as per here we can see this, it is soluble in the alkali but it is insoluble in the acid, dilute acid, and also the soluble fraction, if the question comes which fraction is soluble in alkali and also acid, the answer would be fulvic acid. So here the fraction of the humus which is soluble in alkali and acid will be humic acid. Okay, now comes the next question. So here are two statements. Okay, so isomorphous substitution of cations by those of different charges but having similar sizes within permissible limits within the tetrahedral and octahedral layer lattice clay minerals leads to development of the net unbalanced charge within the lattice. Okay, this is the first statement. The second statement is isomorphous substitution within the aluminum octahedra and silica tetrahedra layers of lower valent cations is substituted by higher valent cations, then having the similar sizes leads to permanent negative charge. Okay, these are the two questions. For this, first we have to discuss what is the major principle of this isomorphous substitution. For this, Goldsmith law is there. Two laws are there. The first law is very important for the in this case. So Goldsmith's first law is, it states that in an ionic crystalline compound, isomorphous replacement of one cation by another without incurring any change in the order of the crystal pattern is permitted, provided that the radii of the cation replaced and the cation substituting it agree within 10 to 15%. And in such isomorphous substitution may lead to a charge imbalance. If in the crystalline structure, since the charge valency of the two cations conserved may differ, thus the substitution of silicon, suppose silicon is +4, okay, in a tetrahedral sheet by aluminium +3 of that, and then the ion in the aluminium ion in the dioctahedral sheet by magnesium +2, that is +3 is substituted by +2 or Fe +2, then the ion will cause excess negative charge in the sheet. This is the charge imbalance, okay, and this is balanced by appropriate or simultaneous substitution elsewhere. So what we get from here, in an substitute ionic crystalline, in an ionic crystalline compound, if there is isomorphous replacement is there, it will be called isomorphous replacement, where one cation, if it is replaced with another cation, the radius difference, the R difference, the radius difference should be within 10 to 15%, not more than that. So it will be called kind of similar, it will be like similar radii, okay. So radius of those cation that should be displaced, and that is the cation that is substituting, the radius differences should be within 10 to 15%, and by this, and after that the substitution of higher valent cation, if suppose in a crystal there is a there is a higher valent cation, suppose +4 or +5. So what happens is, whenever we substitute this with lower valent cation, suppose +3, so in total amount of the crystal there will be a negative charge. How? So removal of +4 and entering of +3. So there will be the one minus negative charge that will be in the crystalline. So whenever excess negative charge is formed, there always will be the higher valency will be replaced by the lower valency. So in that question, the first statement was that the isomorphous substitution cation by those different charges having similar size with permissible limit, that is okay. Then within the tetrahedral and octahedral layer and lattice lamina leads to the development of net unbalanced charge. Okay, so this statement is correct. Statement 2 is isomorphism within the aluminium octahedra and silica tetrahedra, the lower valent cations by the higher valent cations. Okay, substitution of lower valent cations by the higher valent cations, so it will be wrong, because as we know that as we just already learned that higher valent cation should be replaced with lower valent cations. By this, the excess negative charge will be formed in that. So this will be false. So the answer will be statement 1. This is true, but statement 2 is false. Okay. Next come the next question, which did the Langmuir develop the basic theory of adsorption of gases on solids with certain assumptions. So first we have to learn the assumptions of Langmuir adsorption theory. Okay. So these are the assumptions. What are the assumptions? That surface solid is made up of adsorption sites, each of which can adsorb one gas molecule. Okay. If another molecule hits the adsorb sites, then the molecule, it is deflected back into the gas. So by this we can understand that the surface charge is the solid surface charge. Suppose it is the solid surface charge. Okay, it is made up of adsorption site. Suppose negative adsorption site. Okay. So in the adsorption site, which can adsorb only one gas, and if another gas molecule try to hit it, it will be just reflect back. Okay, it will be deflected. Okay, so this is the first assumption. Then comes the second assumption. This is the all the adsorption sites are identical in their affinity for that gas molecule. Okay, this is also all the adsorption sites are identical. That means this site, this shows some affinity with this gas molecule, this site also shows some affinity, this site also shows some affinity, and for a gas molecule each site has the similar affinity with the gas molecules, and these are identical affinity. Okay, and the third assumption is the presence of a gas molecule on the site does not affect the properties of the neighboring sites. Okay, so this means whenever there is a, let's see, there is the adsorption site is there and there is a gas molecule present here. Okay, so gas molecule is present here, but it will not affect the neighboring site, that is this, it will not affect, it can easily attract or it can easily adsorb another gas molecules. Okay, so the third assumption is presence of a gas molecule on one side does not affect the other sides neighboring it, and the rate of adsorption is proportional to the number of adsorption sites, and the pressure of the gas, and the rate of desorption is proportional to the number of occupied sites. Okay, so here we can see that the rate of adsorption is proportional to number of occupied sites, means number of adsorption sites. So adsorption will be more, the adsorption rate will be more when there will be more adsorption sites. Okay, when there will be more adsorption sites, there will be the adsorption will be more, and where will be less adsorption site, so the adsorption rate will be less. And the pressure of the gas also matters here. If the pressure of the gas is high, okay, if the pressure of the gas is high, the adsorption will be more. If the pressure of the gas is less, the adsorption will be less. And also the desorption is proportional to the number of occupied sites. Means if the occupied sites are more, then the chances of desorptions will be more, because it will the gas molecule will not get enough space to get adsorbed. So this is the fourth assumption. So now comes to the Langmuir developed the basic theory of adsorption gas. Okay, so assumptions were, the first assumption is surface will be made up of adsorption sites. Okay, each of which can adsorb one gas molecule. That is okay, true. The presence of gas molecule on one side does not affect the properties of the neighboring side. It is also true. All the adsorption sites are different in their affinity. No, it is not. It is wrong. That we already just learned that it has similar or identical affinity for that gas molecule. Okay, the rate of adsorption is proportional to the number of adsorption. It is true, and the pressure of the gas. Okay, it is true. So A option is correct, B is correct, D is correct. A, B, D. So this option will be correct. Now comes two statements, one assertion and a reasoning type. Dioctahedral mica fixes potassium more strongly than trioctahedral mica. And what is the second reason? What is the reason? More tetrahedral rotation in trioctahedral micas cause shorter KO bond and strong affinity to the potassium compared to the dioctahedral mica. Okay, so first we have to learn the what is the this dioctahedral mica potassium fixation is. Okay, so what happens is, whenever the potassium is attached in the ditrigonal cavity, that is when the bonding, then the bonding behavior of the interlayer potassium in the micas can be ascertained in the dioctahedral B spacing. The dioctahedral B spacing dimension is shorter than the trioctahedral B spacing dimension. Okay, so dioctahedral B spacing dimension is shorter. So what happens? The tetrahedral rotation that occurs, tetrahedral rotation, that is more in the dioctahedral mica. So in dioctahedral mica, the tetrahedral rotation will be more. So when the rotation will be more, the distance from the potassium to the inner oxygen will be shorter. That means the KO bond length will be less in the dioctahedral mica. So what was the option there? Dioctahedral mica fixes potassium more strongly. It is true. Yes, more strongly than the trioctahedral. More tetrahedral rotation in no, it is not true. In dioctahedral, actually more tetrahedral rotation is there. Because what is the reason? Reason is the B space, the dioctahedral B dimension is shorter than the dioctahedral B dimension, that's why. So this will be incorrect. If the option was more, more tetrahedral rotation in dioctahedral micas causes shorter K bond than the affinity of the trioctahedral mica, then if the option is dioctahedral mica here, so the reason will be correct, but the reason is false. So A is true and R is false. This is the answer. Okay. Now comes the next question. It is a calculation type of questions. You have to learn it, and these simple calculations come to the exam, and it is very easy to do. Given a 1000 ppm stock solution of copper sulfate, okay, calculate the volume required from the stock solution to prepare 250 ml of 50 ppm solution through dilution. Okay, so the question is, we have a stock solution that we already we just keep that by preparing it earlier. That is stock solution, its concentration is 1000 ppm, and after that we have to make another 250 ml of 50 ppm solution. So another volumetric flask we take, that is 250 ml, and here the concentration should be 50 ppm. Okay, so how to calculate this? The calculation is done with this equation, that is V1 is 1 is equal to V2 is 2, means the volume of the first solution, that is the stock solution, the volume of the stock solution and the concentration of the stock solution, the multiplication of that will match or will be equal to the another solution that we prepare, that is the volume of that solution with the concentration of the new solution. So here the volume of that solution, that is the question. The question is, calculate the volume required from the stock solution to prepare the 250 ml 50 ppm solution through the dilution. So first we have to take some amount of volume into this conical flask of 250 ml, right? So here V2 S2. So here V2 is 250 ml. Okay, S2 is the final solution, final ppm, final concentration was 50 ppm. Okay, so and here S1 is 1000 ppm, and by this equation we can calculate that 1000 into x is that volume that we should take, and this is 250 into 50, then the x is 12.5 ml. So by this we can get that 12.5 ml from this stock solution. If we take these into the volumetric flask of 250 ml, then make up the volume with water to 250 ml. So this, the concentration of that will be 50 ppm. So come to the next question. So the option will be 12.5. Okay, so now the next question. Given below are two statements, one is labeled as assertion and another is reasoning. Okay, gypsum is commonly used for the reclamation of sodic soil. That is true. Then reclamation process involves reduction in exchangeable sodium with the calcium and its removal from the soil solution through leaching. Okay, first we have to learn what is the gypsum, what is the reaction of gypsum with the sodic soil. So what happens is, here when the soil clay contains sodium ion, it is then the gypsum, that is calcium sulfate. Okay, gypsum is calcium sulfate. This calcium replaces this sodium by forming calcium and soil clay. Okay, then the sodium comes out and react with the sulfate, and it becomes sodium sulfate, and this sodium sulfate is leachable. So it can be leached with irrigation water or ponding the land. By this it will be leached. So the application of gypsum normally applied as brought. This is the more information we should know about the gypsum application, because the direct question can come from this gypsum application, that how it is applied or how it is done, the procedure of that. So gypsum normally applied broadcast, and then incorporated into the soil by disking or plowing. Means we have to mix that gypsum in the soil in the upper layer of the cultivated land, and it is more effective in the removal of exchangeable sodium, okay, than when applied on the soil on the surface. So whenever we put on the surface, it is not that effective than the effectiveness that we see in the plowing layer, or we after applying, if we plow this or mix it, then the effect is more than the just applying to the on the surface. Then mixing limited quantities of gypsum, mixing the limited quantities of gypsum in shallower depth more beneficial than mixing it with deeper depth. Okay, so this question can come also, that mixing of gypsum is very much is more beneficial in which depth, shallower or deeper. So shallower depth, it is in shallower depth it is more beneficial, and in deeper mixture what happens is, deeper mixing exposes the gypsum to react with sodium carbonate. This gypsum will react with the sodium carbonate of that, okay, Na2CO3. So Na2CO3 in the deeper layer, the gypsum will mix with is exposed, and this will react with sodium carbonate, and resulting in the lesser reduction of ESP, because most of the gypsum will be reacted with sodium carbonate, so it will be consumed, the gypsum will be consumed. So if the material is consumed, the effectiveness will automatically reduced. So the ESP throughout the depth, reduction in ESP will be less, and in shallow mixing what happens, soluble carbonates move down with the wetting front without reacting with applied gypsum. In shallow depth what happens, sodium carbonate, the soluble carbonates, any kind of carbonates can move down, okay, so it moved down, so it will not react with gypsum. And what is gypsum requirement? It is the quantity of gypsum that is necessary to reclaim sodic soil, okay. It depends on the total quantity of the sodium present in the soil, okay. And if it is desired to replace larger quantities of adsorbed sodium, then the quantity of gypsum can be accordingly increased, okay. These are the gypsum requirement equation, and the application of gypsum, okay. So the option will be commonly used for reclamation of sodic soil, it is right. Reclamation involves reduction in exchange sodium with calcium and its removal from soil solution through leaching, it is also right. So both option A and option B are correct, and it is the true explanation or correct explanation. Now comes the next question. The cation exchange capacity heterovalent system, which is more practical value than the homovalent ion exchange system, was propounded by, this answer is Gapon. This is a very important question, because the heterovalent system is much more practical in soil than the homovalent system. This was propounded by Gapon. Previously Kerr and Vanslo used to do it more focus, used to more emphasized on the homovalent cation exchange, but in soil actually what happens, the heterovalent or the different charge valency cations are mainly adsorption, mainly exchange sites are occupied with the different valency of cations. So Gapon is the right answer, and it is a very important question, direct question. What is the characteristics of Helmholtz layer in the double layer? Okay, so it is mainly the characteristics regarding enthalpy and entropy. Okay, first we have to learn what is the Helmholtz layer. Helmholtz double layer model, there are 3 double layer models, okay. Helmholtz double layer model, the second one is Goy-Chapman diffuse double layer model, and the third one is Stern model. So in Helmholtz double layer model what happens, the negative charge of the surface colloid is considered to be evenly distributed over the surface. So the negative charge on the surface is evenly distributed to the surface. Then the total counter charge in the second layer is condensed in a plane parallel to the surface of the distance x. So the counter charge, the positive charge are condensed. That means it is very near to the surface in the distance of x, okay, very near. Its distance is x, is small. Then here the separation of the opposite charge is minimum. Separation of the opposite charge is minimum, that is x is very small. So that's why the entropy of the system is also be minimum, because the randomness is low, and the free energy is not minimum as required for spontaneous process for equilibrium. also the separation of the minimum, the system is minimum, some enthalpy is also minimum. Okay, due to the lesser distance, the opposite charge, the separation is minimum, so the entropy is also minimum, that is ion movement is less, that's why the entropy is minimum, and enthalpy is also minimum because the distance is also less. So these are both the enthalpy and entropy will be minimum. And the surface potentials, potential is as a function of the distance from the surface, is at maximum at the surface and drops off linearly with the distance from the surface. The concentration of anion in the Helmholtz surface layer is 0, and the excess cation charge at the surface is determined by the charge density of the solid. So what does it say? That the surface potential of that, if we take a graph of the potential, okay, so here is surface potential this side and here is distance, okay, that is x this side. So what happens is the surface potential is maximum at the surface, and due to it is the counter ions are very near to it, the surface potential suddenly drops. So it is a sharp drop, okay, this is the sharp drop of surface potential. So in this case the surface potential drops very sharply. So from this Helmholtz layer, three major important points are there. The first point is, it is the double layer theory where the surface has the common equivalent charge, the evenly distributed charge. Then comes the cations are also there, and also the when the enthalpy and the entropy is counted, both are minimum. And by this, and the other two layer that I have already said na, that is the Goy-Chapman layer. Okay, the Goy-Chapman diffuse double layer, where what happens is the surface has negative charge and the positive charges are in a diffused form in the bulk solution. This is the Goy-Chapman, and when comes to Stern, it is kind of admixture of those two concepts. What happens is some of the charges are condensed, the counter charges are counter and cations are condensed, and some of the cations are diffused. Actually this is Stern model is actually very practical in the actual case of the soil. Okay, now on the next one, arrange the liming material based on their decreasing neutralizing value. We have to learn the what is neutralizing value. This is defined as the acid neutralizing capacity of a liming material, okay, and as a weight of percentage of calcium carbonate. And this liming material, the 50% of those liming material should be small enough that it should pass 60 mesh sieve, that is the particle size will be less than 0.25 millimeter. These are the neutralizing values of the calcium or calcium carbonate equivalent of those liming materials, that is calcium oxide 179. Okay, so what were the options? Calcium oxide highest, okay, so D will be first, 179. Then comes the calcium hydroxide is second, okay, calcium hydroxide is second, then dolomite, then calcite, or and last basic slag. So calcium oxide first, then calcium hydroxide will be second, then dolomite, okay, Da, then calcite, okay, and then last is basic slag. So DACB, this will be the right answer. So now come the next question. So which of the following are the main assumptions of the theory of diffuse double layer? So let's see the assumptions what are presented here. The charged particle has a flat surface without edge effect, making it effectively infinite in extent. Okay, this is the correct assumption. The exchange sites are randomly distributed, leading to a non-uniform surface charge density. This is wrong. Okay, this is wrong. Exchange sites are actually evenly distributed and it has uniform surface charge. This is the assumption of diffuse double layer. Okay, the dielectric constant of the water is aqueous phase is constant. This is also right, and the ions act as point charge. This is also right. So A, C and D is right. A, C and D. See, option C will be correct. Now comes the next question. The potassium fixed at interlayer position is least available to plants. Yeah, that is true. The potassium which is fixed in the interlayer, that is least available to plants. And the next option is the concept of intensity and quantity and buffering power was given by Beckett. It is also true. So this is also, the option A is true, option B is true. Potassium fixation highest in vermiculite, yes, this is also true. An application of ammonium fertilizer before potassium fertilizer application increases potassium fixation, no. Ammonia and potassium has the similar radii, so it is not true that application of ammonia fertilizer before the potassium fertilizer will fix the potassium. Okay, so this is not true. So ABC will be the answer. And here is the quantity that here was mentioned, the concept of intensity and quantity of the and the buffering power. This is this you should know for the concept building, that the quantity intensity is a plot where delta K exchange and activity ratio of potassium are plotted. What happens? The some subsamples of a soil are taken, means a number of soils are taken, samples, then a different gradient of potassium doses were done, and by seeing the solution potassium before before equilibration and after equilibration, this delta K exchange is found, and the activity ratio is calculated by that, by the activity of calcium, activity of potassium by root over activity of calcium and magnesium, and by this graph or this plot is made, and here the slope is actually the potassium buffering capacity, and the point where the delta K exchange becomes positive, at which at that ARK value where delta K exchange become positive is known as the ARK equivalent or activity ratio of potassium equivalent, that is ARKE. Okay, these are some new extra information regarding this. Now comes the most commonly used urease inhibitor. Okay, let's see what are the nitrification inhibitor examples and what are the urease inhibitor examples. So commonly used chemical nitrification inhibitors are NSAR. You have to remember the chemical name, that is 2-chloro-6-trichloromethyl pyridine, and for AM 2-amino-4-chloro-6-methyl pyrimidine. Okay, these two you have to definitely remember that. NSAR, the nitropyrin 2-chloro-6-trichloromethylpyridine, or AM 2-amino-4-chloro-6-methyl pyrimidine. Then DCD, diazonamide, and 4-amino-1,2,4-triazole, that is ATC. Okay, these are the examples of nitrification inhibitor. Urease inhibitor are phenyl phosphorodiamidate, PPDA. Then NBPT, N-butyl thiophosphoric triamidate, and PMA, that is phenyl mercuric acetate. Okay, then quinone benzoquinones. Okay, quinone benzoquinones. These are also the example of urease inhibitor. Now see the options. Here the NBPT, okay, NBPT was urease inhibitor, and phenyl phosphorodiamidate PPD, it was also PPD, yeah, this one. Okay, so yeah, this one also was urease inhibitor. Then comes hydroquinone, this is also urease inhibitor, and dicyanamide, this was actually nitrification inhibitor. Okay, so A, B, C will be the answer. A, B and C. Okay, so in 12, question number 12, the A answer will be correct. Now the next question comes, hidden hunger. Hidden hunger is the visual deficiency. No, in hidden hunger we cannot see the visual deficiency, that's why it is hidden. Severe yield reduction may occur without the appearance of the deficiency symptom, this is correct. Okay, so this is the actual definition of hidden hunger. Hidden hunger is the when we cannot judge by seeing the or observing the deficiency symptoms, but after yield or after cutting harvesting, if we count the yield, then we will see there is a huge reduction. That's what the hidden hunger means. That means the hunger was there, but it was hidden. That's why we couldn't see in our naked eyes, or we could not observe on the visual basis. Now comes interveinal chlorosis first and older leaves. Okay, in older leaves or younger leaves, which kind of deficiency will be seen in the older leaves, and which can be which elements or which nutrients deficiency will be seen in the on the younger leaves. So for this we have to know the mobility of the nutrients in plants. Okay, so in plants, mobile nutrients are chlorine, manganese, molybdenum, nitrogen, phosphorus, potassium. Okay, and for immobile, that is boron, calcium also, copper. Manganese is actually moderately mobile, and then iron is immobile, sulfur is immobile. So whenever the question comes in older leaves, means in a plant, this is the older leaf, okay, and this is the younger leaf. In a plant, what happens is, when the root takes that nutrients, so it moves first, if it is mobile, if it moves first to the younger leaves, okay, then what happens, the older leaf gets starvation. So here the interveinal chlorosis first observed in older leaves mean the nutrient should be mobile in plant. So here the mobile nutrient is magnesium. Okay, the question can be in the reverse form, that is the chlorophyll on the younger leaves, then we have to judge what is the immobile nutrient on the option. So if what happens in the immobile nutrient, because it is immobile, it is the rate of moving is slow, so it can reach up to the older leaves only. So younger leaves get starvation. Now comes the activity index used to evaluate the solubility of urea formaldehyde compounds. Okay, this equation you have to definitely remember. This direct question comes that is the percentage of CWIN minus the percentage of HWIN by the percentage of CWIN into 100, where the CWIN is the percent nitrogen that is insoluble in cold water. Okay, percent nitrogen that is insoluble in cold water insoluble, and it is HW means insoluble in hot water insoluble. The question may come from this also, that here the temperature, what is the temperature is of the cold water and what is the actual temperature of the hot water is considered here. Cold water is the room temperature water, that is 25 degrees Celsius, and hot water is around that boiling point, that is 98 to 100 degrees Celsius. Okay, these are the small details you have to remember that. So here the option will be CWIN minus HWIN. Okay, this will be the answer. Okay. Now comes, arrange the following, increase the amount of nitrogen in the fertilizer. Okay, so we have to know the nitrogen content of those fertilizers. Here are the options, okay, of those ammonium sulfate, that is 20.5%. okay, ammonium sulfate is 20.5%. okay, ammonium sulfate is 20.5%. then comes the ammonium chloride at 25%, then ammonium nitrate 34, calcium ammonium nitrate, that is 25%. okay, so by this we can arrange that ammonium sulfate from what is, it is increasing order. So lowest is ammonium sulfate, so A will be first option. Then comes the ammonium chloride. Okay, ammonium chloride comes, then so C will be the second option. Then comes the calcium ammonium nitrate 25%, so it will be D, and the ammonium nitrate, the 34% is the correct answer. So the correct answer will be ACDB. Okay, next come to the next question. Match the following, the essentiality of nutrients, and which scientist gave that. You have to remember this chart. It is very easy to remember. The hydrogen, oxygen and carbon, it was discovered very earlier, okay, since immemorial. Carbon was this hydrogen, oxygen since immemorial. Carbon was by Priestley, okay, carbon was by Priestley, and nitrogen by Theodore de Saussure. Okay, These two you can remember very easily, priestly carbon and nitrogen theodate. Then the four group, see, potassium, calcium, magnesium and phosphorus. Okay, PKCAMG, PKCAMG. These all were the essentiality was discovered by Sprengel. Okay. Then comes the sulfur, that is Sack and Knob. You have to remember that. Chlorine and iron is very important, Egris. Okay. Boron is Warrington. Manganese Macharge. Okay. MnMc manganese Macharge. Zinc for Somnan and Lipman. For copper, Soman, Lipman and McKinney. For copper. And for molybdenum, Arnon and Stout. And nickel, it was Welch and Carey and Brown. Okay. So by this we have to remember very important. This is a very important chart to remember. So here we can match that. So first, molybdenum. Molybdenum is Somnar and Lipman. Okay. No. Molybdenum is Arnon and Stout. Okay. Zinc is Soman and Lipman. Sulfur is Sack and Knob. And the carbon is Priestley. Okay. So the option will be 3, 4, 1, 2. 3, 4, 1, 2. This option will be correct. Now the next question. The nutrient and its enzymes that is related, that is affected by those nutrients, that copper, iron, zinc and molybdenum. First we have to know those micronutrients, the function of those micronutrients. So zinc, copper and manganese, these are involved in the carbohydrate and protein metabolism. Okay, carbohydrate protein metabolism through several enzyme system. So zinc, copper and manganese. Okay, zinc is involved in some of the growth promoting hormones like auxins and the reproductive process of many plants which are very vital and grain formation. The most important metalloenzymes with zinc associated: zinc, carbonate anhydrase, dehydrogenase, proteinase and peptidase. Okay, iron containing is cytochrome oxidase, catalase and peroxidase. Then copper containing it also cytochrome oxidase and ascorbic acid oxidase and polyphenol oxidase. You have to clearly remember all the different enzymes related to the different micronutrients. So manganese, it is actually all decarboxylase, dehydrogenases of the TCA cycle. Okay, and molybdenum is associated mainly nitrogenase and nitrate reductase. Okay, molybdenum is very important. It is associated with nitrogenase and nitrate reductase enzymes. Okay, then nickel is a component of urease enzyme. And boron is associated with the rate of water absorption and translocation of sugar. So now come to the answers. First is copper. So copper is ascorbic acid oxidase and phenol oxidase. No, this is the answer. Okay. Then comes iron. So here iron will be catalase peroxidase. Okay, the iron will be catalase peroxidase. Then comes zinc. Zinc is carbonic anhydrase and dehydrogenase, and molybdenum was nitrogenase and nitrate reductase. Okay, the answer will be 2, 3 and 4. 2, 3, 4, 1. Okay, this will be the answer. Now comes the next question. Manganese. Okay, which of the following is not a criteria for essentiality? Okay, we have to remember first the essentiality criteria. The first criteria was it should be mostly directly involved in the plant metabolism. Yes, this is right. It should be directly involved with the plant metabolism. And then comes the nutrient must be replaceable by another element. No, this is not right. Actually, the essentiality, the criteria was this particular nutrient cannot be replaced by any other nutrient. Okay, the function of that nutrient will be recorrected or will be then again the function of the can be recovered or can be matched with the only that nutrient only, not be replaced with the another element. The plant cannot complete its life cycle in absence of the nutrient. This is also correct. And the nutrient must have a specific physiological role in plant growth. Okay, this is also correct. So option C will be false, which is not a criteria. Okay, option C will be the option. Now comes given below are two statements. Okay, diffusion is a principal supply mechanism for the nutrients Pk, iron and zinc. Yes, this is true, diffusion. And reason is diffusion is movement of nutrients through water from an area of higher concentration to lower concentration. Okay, so this is a perfect explanation of that. And the thing is the diffusion happens where there is no any membrane is there. So diffusion happens in the clear area, or what can I say, that if something is there, I mean if a solution or media is given here, if the concentration is high here, it will diffuse in the whole place. Okay, so from the higher to lower to make it even distributed. Okay, this is the diffusion function. Come to the next. Dehydrogenation activity reflects the total range of the oxidase. Okay, total like the oxidative activity of the soil microorganism and may be considered a good indicator of the oxidative metabolism in soil. Yes, this assertion is true. Why this happens? Dehydrogenases oxidize the soil organic matter by transferring the protons from and electrons from the organic substrates to the inorganic acceptors. Okay, by this it oxidizes those organic matter by the transferring of the protons and the electrons from the organic substance to the inorganic acceptors. So this is the perfect explanation of assertion A1. So the option 1 will be correct. Okay, correct explanation. Here are the statement enzymes which are distant from the point of origin are termed as extracellular. Yes, this is true. Extracellular, intracellular, extracellular when the enzyme is formed somewhere else but it works in the different place, that is extracellular. And also the statement 2 is enzyme which are produced in constant amounts without regard to the concentration of the substrate are termed adaptive. No, this is not true. Two types of categorization we can derive that. One is constitutive, one is adaptive. Okay, constitutive means it doesn't matter if there are any substrate or not, the enzyme will produce itself. And the adaptive enzyme is if there is need, if a substrate is there, then the enzyme will be produced. So here it will be constitutive actually, not adaptive. So 1 is true and the 2 is false. Okay, this will be an answer. Now comes NSQ. NSQ is the needle slag, setting with speed and quotient, that is combines meteorological parameters. It comes with rainfall and temperature. Okay, this is the option, rainfall and temperature. So for this more information we should know that if the NSQ is less than 100, it is actually arid. Okay, see, it is arid, and also the CN ratio is low carbon content is there. Organic carbon is also low. Okay, organic carbon is also low. So NSQ, by the different range of NSQ we can say that if it is arid or semi arid or humid or parhumid, so less than 100 arid, 100 to 200 then it is semi arid, 200 to 400 then it is humid, and parhumid is more than 400. And with the increase in NSQ also the organic carbon increases. See, okay, organic carbon and percentage of nitrogen also increases. Which of the correct descending order of CN ratio? Okay, so CN ratio means whichever has the largest size will have the more carbon content or organic matter in that. So in that case, in actinomycetes bacteria and fungi has the huge amount of carbon rather than the actinomycetes, then actinomycetes and then bacteria. So this will be the correct formation. The CN ratio, this is a very important question, the CN ratio, and also the which is the dominant organism. These are some questions that comes very regularly in those exams. So fungi, actinomyces and bacteria will be the correct order, descending order. Okay, which group of the bacteria is more dominant in the rhizosphere? Okay, in rhizosphere, this is also very important question. Even last year also this question comes, I guess. The group of bacteria that is mainly dominant in rhizosphere is the non-spore forming gram negative. Okay, non-spore forming NS, gram negative G. Okay, just clearly remember that non-spore forming, that no spore formation is there, and it is gram negative. And a gram staining gram staining test, it will be negative. Okay, the result will be negative. So now comes the next question, the biochemical reduction of the nitrate under anaerobic condition. Okay, biochemical reduction. where biology will be also utilized, means soil by microbiology all will also contribute. So it will be denitrification of the biochemical energy, it will be denitrification. So see, denitrification is a process limited to an oxic soil in which bacterial reduction, okay, bacterial reduction of nitrate to nitrite takes place, leading to the release of NO, N2O and nitrogen gas. However, the relative proportion of the resultant gases could vary considerably. Some of the organisms that are involved in the denitrification, this question may also can come, that is Thiobacillus denitrificans, Thiobacillus thioparas and Pseudomonas micrococcus, Achromobacter bacillus also, okay. So this is a denitrification process, which is a biochemical process. Now comes the resistant spore produced by cyanobacteria. It is very important, it is akinete resistant spore, okay. Cyanobacteria, the resistant spore that is formed, that is akinete. So two statements are there. The activity of aerobic bacteria remains unaffected under anaerobic condition. No. In aerobic bacteria, actually the activity of aerobic bacteria mainly only they survive in the aerobic condition. Whenever the anaerobic condition arises, so it will get affected very badly, okay. And the facultative anaerobic bacteria use aerobic respiration but can switch to anaerobic. Yes, this is the actual definition of facultative anaerobic bacteria, which use the aerobic respiration can switch according to the situation. So statement 1 will be correct and statement 2 will be false. So this answer will be correct, okay. Now come, which of the following is a phosphate solubilizing? This is also a very frequently asked question. This is the bacillus, okay. You have to remember that these are the most expected question that we can expect in the exam also, that ICAR PG exam. So this is a very direct type of question in soil science. What happens is they sometimes go for very easy questions, but what happens is in the exam situation we sometimes forget the very obvious questions. So these are the some questions that is very important, that is repeated many times. If the question is said based on the previous year questions, then this question will come definitely, okay. Now the list, that is what is phototroph, organotroph, lithotroph, chemotroph. First we learn it. Phototroph is organism that use radiant energy, okay, that is phototroph. Organism that utilize the chemical energy, that is chemotroph. Organism that oxidize an organic form of carbon is called heterotroph, okay. And lithotroph are organism that oxides inorganic compound, that is lithotroph, okay. So in that question, what was that? Phototroph, okay. So what was phototroph? Phototroph utilizes the radiant energy, okay. Now comes organotroph, it utilizes organic compound. Then lithotroph, it utilizes the inorganic compound, and chemotroph utilizes the chemical energy. So the option will be option D. Some more information regarding this, the metabolic group of the organism, that is photolithotroph. Photo means it will use the energy obtained from light. Litho means the electron source will be reduced mineral, okay. Energy source and electron source. Photolitho means photo means energy will be obtained from light, and litho means reduced mineral will give the electron, okay. Photoorganotroph. Photo means it will ATP generated by photosynthesis, like the same of the previous. Organotroph means organic carbon is the electron source, right. Now comes the photoaquatroph. It is also similar. Photo means the ATP generated by photosynthesis, and the electron source is here aqua, that is water. And chemolithotrophs, here the energy is actually from chemical oxidation, okay, chemical energy. So it is chemolitho. Litho means the electron source will be from the inorganic ions. And the chemoorganotroph, okay, here the electron source is actually organic carbon compounds, okay, and energy will be chemo, means chemical oxidation energy, and the electron source will be organic compound. So these are the most important and can be the expected 30 questions from those parts. Thank you very much for watching this video, and I will see you in the next class. Thank you.